Introductory Statistics, Module 7, the Normal Probability Distribution. Section 7.1, Properties of the Normal Distribution. We will look at these four objectives in this section. Objective 1, we want to use the uniform probability distribution. So let's look at an example illustrating this. Suppose that United Parcel Service is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. The delivery could be at 10 a.m. x is 0, or at 11 a.m. where x is 60, with all 1 minute interval of times between x is 0 and x is 60 equally likely. So that's to say, your package is just as likely to arrive between 10:15 and 10:16 as it is to arrive between 10:40 and 10:41. The random variable x can be any value in the interval from 0 to 60. Because any two intervals of equal length between 0 and 60 inclusive are equally likely, the random variable x is said to follow a uniform probability distribution. A probability density function is an equation used to compute probabilities of continuous random variables. It must satisfy the following two properties. 1. The total area under the graph of the equation over all possible values of the random variable must equal 1. And 2. The height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. The graph below illustrates the properties for the time example. Notice the area of the rectangle is 1, and the graph is greater than or equal to 0 for all x between 0 and 60, inclusive. Because the area of a rectangle is height times width, and the width of the rectangle is 60, the height must then be 1 over 60. Values of the random variable x less than 0 or greater than 60 are impossible. Thus, the function value must be 0 for x less than 0 or greater than 60, as we see here in the picture. The area under the graph of the density function over an interval represents the probability of observing a value of the random variable in that interval. So the probability of choosing a time that is between 15 and 30 minutes after the hour is the area under the uniform density function. So notice in the picture that the width of the shaded rectangle is 15, since 30 minus 15 is 15. And the height is 1 over 60. So we'll multiply 15 times the 1 over 60 to get a value of 15 over 60. Which will reduce down to 0.25. So the probability of choosing a time between 15 and 30 minutes after the hour is 0.25. Objective 2, we want to graph a normal curve. Relative frequency histograms that are symmetric and bell-shaped are said to have the shape of a normal curve. If a continuous random variable is normally distributed, or has a normal probability distribution, then a relative frequency histogram of the random variable has the shape of a normal curve, which is bell-shaped and symmetric. We see here that the highest point is our mean in the middle, and we have inflection points, or a change in the direction of the curve of our line, at the mean minus the standard deviation and the mean plus the standard deviation. So let's look at the effect first here in this top picture of changing the value for the mean. We see that changing the value of our mean from 0 to a value of 3 and leaving the standard deviation the same causes our graph to shift 3 units to the right. Now in the bottom picture here, we are leaving the mean the same but changing the standard deviation. So we've changed our standard deviation from 1 to 2. And increasing the standard deviation caused the graph to be shorter and more spread out. Objective 3. We want to state the properties of the normal curve. First, it is symmetric about its mean, mu, which means that if we folded it in half on that line in the middle, each side would lie on top of the other. So each half is the same. Second, because the mean equals the median equals the mode, the curve has a single peak and the highest point occurs at x equal the mean. 3, it has inflection points at the mean minus the standard deviation and the mean plus the standard deviation. 4, the area under the curve totals to 1. 5, the area under the curve to the right of the mean equals the area under the curve to the left of the mean, which equals 1/2. So the mean divides the curve exactly in half. 6, as x increases without bound, or gets larger and larger, the graph approaches but never reaches the horizontal axis. As x decreases without bound, gets more and more negative, the same is true. The graph approaches but never reaches the horizontal axis. And number 7, the empirical rule is true. Approximately 68% of the area under the normal curve is within 1 standard deviation of the mean. 95% will be within 2 standard deviations of the mean, and 99.7% is within 3 standard deviations of the mean. And here we see a picture of our normal distribution curve. Objective 4. We want to explain the role of area in the normal density function. So let's look at an example. The data on the next slide represent the heights in inches of a random sample of 52-year-old males. First, we want to draw a histogram of the data using a lower class limit of the first class equal to 31.5 and a class width of 1. And then we'll look to see if the variable height of 2-year-old males is normally distributed or not. So here we see our data, which is our heights of 52-year-old males. And here we see a histogram of that data. So the lower class limit of the first class was 31.5 with a class width of 1 each time. The height is on the horizontal and the percent of that occurring is the heights of the bars, and that is on the vertical. In the next slide, we have a normal density curve, which we'll draw over top of the histogram we just saw. And we want to answer this question. How does the area of the rectangle corresponding to a height between 34.5 and 35.5 inches relate to the area under the curve between these two heights? So here we see our picture. This is the histogram we looked at before, except now we've drawn over top of it a normal density curve. And notice here we're going to highlight the bar that's between 34.5 and 35.5. Notice that the area of this shaded region is very close to the area under the normal curve for the same region. So what that allows us to do is to be able to use the area under the normal curve to approximate the proportion of 2-year-old males with heights between 34.5 and 35.5 inches. So let's look at the area under our normal curve then. Suppose that a random variable x is normally distributed with mean mu and standard deviation sigma. The area under the normal curve for any interval of values of the random variable x represents either the proportion of the population with the characteristic described by the interval of values, or the probability that a randomly selected individual from the population will have the characteristic described by the interval of values. So let's look at an example. The weights of giraffes are approximately normally distributed with a mean mu equal 2,200 pounds and a standard deviation sigma equal to 200 pounds. First, we want to draw a normal curve with the parameters labeled. So we'll draw a curve, and it doesn't have to be perfect. And we're going to put the mean in the middle, which was 2,200 pounds. And then I'm going to go out 3 on either side of that, standard deviations. So going to the right, I'm going to add 200 pounds each time. And going to the left, I'm going to subtract 200 pounds. So here I'll have 2,400, 2,600, and 2,800. Here I have 2,000, 1,800, and 1,600. Now we want to shade the area under the curve to the left of x equaling 2,100 pounds. So that's going to be exactly between 2,000 and 2,200. So we're about right here. That would be our 2,100. We want to shade to the left of it. Now I want to suppose that the area under the normal curve to the left of x equal 2,100 pounds is 0.3085. And we want to provide 2 interpretations of this result. We're going to assume then that the area here was 0.3085, this shaded part. So we know that then either the proportion of giraffes whose weight is less than 2,100 pounds is our 0.3085, or that the probability a randomly selected giraffe weighs less than 2,100 pounds is 0.3085.